Okay, guys, how's it going? Welcome back. Today we're going to be learning about rational exponents. Rational exponents. Pretty easy stuff. Just a little hint. Freshen up on your fraction skills because rational exponents basically mean that there are fractions in the exponents. So we're going to have to, add and subtract and multiply them together and whatnot. So please refresh your fraction skills. Remember that I do have a fraction video in my Morals Math corner in YouTube. Anyways, all right, guys, you can write a radical expression in an equivalent form using a fractional or rational exponent instead of a radical sign. For example, in general, the nth root of x, remember n is the index, equals x to the 1 over n. Now, let's just remember really quickly that every number in the world is being multiplied by an invisible 1, divided by a 1 that's invisible, and it's also being raised to the first power. So basically what happens here is when I have the nth root of x, I have the exponent of the radicand as the numerator and the index as the denominator. Again, I have the exponent of the radicand as the numerator of the exponent, and I have the index as the denominator of the exponent. It's pretty easy. Okay, and this is for any positive integer n. Like the radical form, the exponent form indicates a principal root, the principal root being the radicand. Now, I know that all of these answers are pretty easy, they're perfect squares, but I just want you in this particular case to just go through the motion of writing an exponent in rational exponent form, or a radical, I'm sorry. I want you to go over the skill of writing a radical as a rational exponent. So we're going to practice radical to rational exponent. So I have the square root of 36. So the base here is 36 to the first power, and the root is 2. So I have 36 to the 1/2. Okay? Cube root of 64. So my radicand, 64 to the 1/3. Yes, I know that this could be simplified and the answer would be 4, but we're not going over that right now. We're just going over the skill of how to go from a radical to a rational exponent. 4th root of 16, the base of 16, the power of the radicand is a 1, the power or the root, the index is 4, so I've got 16 to the 1/4. Okay. What is the simplified form of each expression? Now, we're going to go ahead and reverse the skill and actually simplify it. So, if I have 216 to the 1/3, that means I have the cube root of 216. Okay, why? What was the power of the radicand? 1. Boom. What was the index? 3. Boom. So, I hope you guys saw that. When I have 16 to the 1/3, or 216 to the 1/3, that's the third root of 216. The power of the radicand, which is what the base equals, that's the radicand, is 1. So that's why I did not have a power for 216, because it's invisible. So the cube root of 216, okay, let's break this up. This is going to be 2 times 108, 2 times 54, and 2 times 27. I'm going to stop right there because I've got a 2, and a 2. So that comes out as a 2 times. The cube root of 27 is 3. So 2 times 3 would be 6. Done. Okay, here we've got 3 to the 1/2 times 12 to the 1/2. Please, it's tempting to add those exponents. You cannot add those exponents because they do not have the same bases. Okay, so please don't do that. But what you can do is write this as square root of 3. This is the square root of 12. All right. We could do one of two things. We can either multiply them together, and that's the square root of 36, which is 6, or you could have said, okay, this is 4 times 3, so this is square root of 3 times 2 square root of 3, which would have been 2 times square root of 3 times square root of 3, which still would have been 6 either way. Okay. Got here 5 to the 1/4 and 125 to the 1/4. Okay. Let's see what I would do here. This is the 4th root of 5 times the 4th root of 125. In this case, let's multiply them together, guys. But watch what I do. This is the 4th root of 5 times 125. Sometimes it behooves you not to multiply the radicand completely because we know we're going to go ahead and reduce it, right? We're going to simplify it. So in this case, this is 5 times 25. This is 5 times 5. Boom, there it is. I got a 5, a 5, a 5, a 5. I got 4 5s in a 4th root, so that comes out as 1 5. I'm done. Okay? I got the square root of 7 times the square root of 7. That's easy. Square root of 7 to square root of 7 is just 7. Because remember, when we multiply the same square roots, the square roots cancel and the radicands pull out as one value. All right. Now, let's go ahead and complicate things a little bit. You know how math loves to do that. We've already been working here. When I have x to the 1 over n, that equals the nth root of x. So again, if I have the 3rd root of x, that equals x to the 1/3. Vice versa, if I have y to the 1/5, that equals the 5th root of y. Okay, that's that. Now, sometimes the power of the radicand is not going to be a 1. So what's going to happen is the following. X to the m over n will equal the nth root of x to the m, or the nth root of everything raised to the m power. Let me explain what that means really quickly. Let's say I have x to the 3/5. That's going to be the 5th root of x cubed. That's the way I like to write it. Sometimes you may see it like this, the 5th root of x cubed. Why would they write it like that? Well, think about it. The 5th root of x, this works out to be x to the 1/5. That's raised to the power of 3. I don't know if you guys remember, but when you raise a power to a power, you multiply the exponents. So that would become x to the 3/5. Because 3 times 1 is 3, and 1 times 5 is 5, so x to the 3/5. So that's how they get that. I do not like this second way that much. You're going to have to know how to recognize it because they're going to write it like this on the SAT or in the book or in the ACT or on different tests. But just do know that this is the way I use it. That is the more popular or common way, and it's a lot easier to understand in my opinion. Okay, for example, let's convert each into radical form. Okay, I've got the 7th root because remember the denominator is the index of x cubed. I guess if you wanted to, you could do the 7th root of x cubed. But again, I like this one a lot better. I'm going to stick to that one. Okay, this is a very good one. This is a very good one. N is negative here, okay? If you remember, when we first talked about this, it said that n had to be, it's in the other page, but it said here that, let's see, let me go back. Yeah, there we go, for any positive integer n. So we got to make that a positive. That's okay. We know how to do this. Okay, we know how to do this. If you remember, you make a negative a positive by bringing it down to the bottom. So this is going to equal 1 over y to the 3.5, which equals 1 over y to the 7/2, which now we can go ahead and rewrite as 1 over the square root of y to the 7th. We can simplify this. This becomes 1 over y to the 3rd over y times the square root of y. How come I took out y to the 3rd? Remember what we talked about. 7 divided by 2, it goes in 3 even times, and I have 1 y left over. I need to rationalize because I cannot have radicals in the denominator, so I'm going to multiply both top and bottom by square root of y. So I'm going to have the square root of y over y cubed times the square root of y times the square root of y is another y. So I have the square root of y over y to the 4th. Okay, absorb that. We're going to do another one right now. W to the negative 5/8. That's going to equal 1 over w to the 5/8, which equals 1 over the 8th root of w to the 5th power. Okay, well, I need to rationalize this. I have an 8th root, so I need a set of 8 to pull out one value. I have 5 w's right now, so I need to multiply by the 8th root of w cubed. The 8th root of w cubed. What is that going to give me now? It's going to give me the 8th root of w cubed in the numerator over the 8th root of w to the 5th times the 8th root of w to the 3rd is the 8th root of w to the 8th. So remember, those cancel. So I'm left with w. I just rationalized. Perfect. Done. Next, w to the 0.2. This is going to be w to the 2/10th, which let's go ahead and reduce. Let's simplify always. W to the 1/5, which equals the 5th root of w. No need to rationalize because that is simply in the numerator. It was a positive exponent, and we did not need to bring it down. Now we're going to add fuel to the fire right now, and we're going to start doing some more complex stuff. And I want to go ahead and give you a brief little mini review of the properties of rational exponents. Okay? So don't stress about that. We're going to go over the review in a second. Let's just do a couple more examples of these. Let's reverse this now. We went from radical form to exponential form. Exponential form to radical form. Now let's go radical form to exponential form. Okay? I think it's going to be nice and easy. Okay. First of all, you can work this a couple different ways. This is going to be a to the 5/2. And actually, we don't want to simplify it at this point. We just want to go ahead and put it into exponential form. We're not asking you to simplify. We're asking you just to write it in exponential form. This here, b would be y to the 4/5. Remember, this 4 really belongs to this guy. C would be x to the 3/4. And d would be b to the 3/5. Remember, the numerator is the exponent of the radicand, and the denominator is the index. Now, let's get to those properties that I promised. Sorry. All right, my friends. All properties of integer exponents apply to rational exponents. So let's have a quick review. Properties of rational exponents. Let a and b be real numbers, and let m and n be rational numbers. The following properties have the same names as those listed on page 330. Okay, but now apply to rational exponents as illustrated. All right, let's talk about this. I don't know what this page 330 is, by the way, guys. I have no idea. But let's go ahead and go over this. When I'm multiplying the same basis, I add the exponents. So a to the m times a to the n is a to the m plus n. If I'm talking about having rational exponents, my friends, if I have 5 to the half times 5 to the 3/2, that's going to be 5 to the 1/2 plus 3/2, which is 5 to the 4/2, which is 5 squared, which is 25. When I have a to the m raised to the n power, I'm going to multiply the exponents. I'm going to distribute it. So I have 3 to the 5/2. I'm going to distribute that 2 to the 5/2. 5/2 times 2 is 5. So 3 to the 5th is 243. Same thing here. When I multiply a product that's inside of a parenthesis, and I raise that product to an mth degree, I have to distribute that m to the exponents of everything inside the parentheses. So I'm going to be left with a to the m times b to the m. So if I have 16 times 9 to the 1/2, I distribute that to both, my friends. That's going to be 16 to the half, which is the square root of 16, which is 4. And that's going to be 9 to the half, which is the square root of 9, which is 3. 4 times 3 is 12. We already saw what happens when we have a negative exponent. We simply bring it down, or vice versa. If I have 1 over a to the negative m, I go ahead and bring it up to the numerator. that would equal a to the positive m over 1. Okay? So if the negative exponent is in the numerator, bring it down to the denominator to make it positive. If the negative exponent is in the denominator, bring it up to the numerator to make it positive. So for example, I have 36 to the negative 1/2. That's 1 over 36 to the 1/2, which is 1 over the square root of 36, which is 1/6. When I have the same base and I am dividing them, I am going to subtract the exponents. So a to the m divided by a to the n is going to equal a to the m minus n. So if I have 4 to the 5/2 divided by 4 to the 1/2, same base, that's going to be 4 to the 5/2 minus 1/2, which is 4 to the 4/2, which is 4 squared, which equals 16. And last but not least, if I have a quotient inside of parentheses and I am raising that quotient to a power, I must distribute that power to all of the exponents inside of the parentheses. So a over b in parentheses raised to the m power will be a to the m over b to the m. So if I have 27/64 to the 1/3 power, that's going to be 27 to the 1/3, which is the cube root of 27, which is 3, and 64 over 64 to the 1/3, which is the cube root of 64, which is 4. So those are my rules that we've already learned, and I know you know them, but I just wanted to review them with you guys. All right, now, if you recall from lesson 6-2, okay, that you simplified products or quotients involving radical expressions only when they had the same index. Remember, we've already been learning that cube root of 2 times the cube root of 7, okay, that's the cube root of 14. But if I gave you the cube root of 2 times the square root of 7, we couldn't do that, okay? We can't do that. Not at this level. Today we're going to learn how to do that, all right? So before, we learned that we can only multiply radicals, and you can only multiply radicals when they have the same index. However, you can combine radical expressions with different indexes if you convert them to rational exponents. So if you go ahead and convert, okay, the same radicands in different radicals to the same radicands with different rational exponents, you can then use your properties of exponents and simplify. For example, before, if you saw a, you would not be able to do this. You cannot divide the 4th root and an 8th root. However, I can convert these to rational exponents. They'll have the same base, and now I can use my rational properties. For example, this is x to the 3/4 over x to the 2/8, which equals x to the 3/4 over x to the 1/4 when I reduce. And guess what? I have the same base x. They're being divided. What do I do to the exponents when I'm dividing the same base? I subtract them. So this is going to be x to the 3/4 minus 1/4, which is going to be 1/2, or square root of x. I hope that makes sense to everybody. Okay, sorry about that. Just had to take a little break there for a second. All right, so B. I have the square root of 3 times the 4th root of 3. I can't do anything like this in this radical form. However, I can do this. 3 to the 1/2 times 3 to the 1/4. Now I have the same base. When I have the same bases, I add the exponents. So 3 to the 1/2 times 3 to the 1/4. It's going to be 3 to the, remember guys, 1/2 plus 1/4. That goes to 4, that goes to 2. So that's to the 3/4. Or the 4th root of 3 cubed. Rational form and radical form. Next, the square root of 7 times the cube root of 7. I can't do anything in this radical format. However, I can do 7 to the 1/2 times 7 to the 1/3. Have the same base, so I add the exponents. 1/2 plus 1/3. That goes to 6 and a 3. That goes to 6 and a 2. So 7 to the 5/6, or the 6th root of 7 to the 5th power. Actually, 6th root of 7 to the 5th power. Either one of those. Okay, square root of x cubed over the cube root of x squared. I'd love to be able to simplify this, but I cannot in radical form. But I can do x to the 3/2 divided by x to the 2/3. When I am dividing the same base, I subtract the exponents. So it's going to be x to the 3/2 minus 2/3. 6, 9, 6, 4. So that's going to be x to the 5/6, which would equal the 6th root of x to the 5th power. Either or, an exponential or radical form, depending on what they ask you. Let's go ahead and continue some more practice. What if I have 16 to the negative 2/5? Well, first thing I'm going to do is, this is 16 to the negative 5/2, okay, which then is going to equal 1 over 16 to the 5/2, which is going to equal, let's see if you can think about it like this, guys. You have one of two things here. The square root of 16 to the 5th, okay, which then, think about it. I'm looking for sets of 2. So I have 5 16s. So that means I have 2 sets of 2. So I could pull out a 16, and I have 1 square root of 16 left over. So that's going to be 16 times 4. So I have 1 over 64. And actually, wait. I think that's wrong, because I have 4 sets of 16. I'm sorry. I'm not paying attention. Instead of trying to do it in my head and be fancy, let me do it out the right way. 1, 2, 3, 4, 5. Okay, I got 16, 16, 16, 16, 16. Let's make this a little bit easier. I got 2 and a 2. Okay, so I got a 16 that comes out times another 16 that comes out times 6 square root of 16, which is 4. So it's going to equal 1 over 1,024. Sorry about that little snafu there, guys. Okay. Next. Let's do this a different method. Everyone has different methods for everything in life. So let's go ahead and do this one a little bit differently. If you want. It's up to you. Let's just go ahead and start this one out. And let's call it the 5th root of, remember this is negative 32 to the 4th power. Okay, it's negative 32 to the 4th power. Just remember that. This is in parentheses, so this can happen. And also remember it's an odd root, so this can happen. This is totally fine. What's happening here is I have negative 32 4 times. So I have a negative 32, and I have a negative 32, and I have a negative 32. Okay? Hope everyone's with me there. Now, in this case, we know that 4 negatives multiplied together, we're going to have positives. So we eliminated the negative problem right there. 32. This is going to be 2 times 16, 2 times 16, 2 times 16, 2 times 16. The 16s break down into 2 times 8, 2 times 8, 2 times 8, 2 times 8, 2 times 4, 2 times 4, 2 times 4, 2 times 4, 2 and a 2, 2 and a 2, 2 and a 2, 2 and a 2. All right, so we got a lot of 2's there. Remember, every set of 5 2's comes out as 1. So I've got 1, 2, 3, 4, 5. So that's 1, 2. Then 1, 2, 3, 4, 5. Another 2. 1, 2, 3, 4, 5. Another 2. 1, 2, 3, 4, 5. Another 2. And my answer would be 16. Now that's the way we just did it. Let me show you another way. show you a little bit of an easier way. If you know your multiplication tables really well, and you know your factors and perfect squares and all that stuff, you can really work this out a lot easier. For example, let's go ahead and rewrite this as the fifth root of negative 32 to the fourth power. Now, how about if we do this, guys? Isn't this the fifth root of, isn't negative 32 negative 2 to the fifth power? So why don't I go negative 2 to the fifth power, all raised to the fourth. Wait a second. The fifth root of negative 2 to the fifth power, those cancel. So I got negative 2 to the fourth power. Negative 2 to the fourth power will equal 16 as well. So there is more than one way to skin this cat. You want to break it down the long way? Fine, you can. That's just no worries with that. You want to go ahead and be savvy and reduce as much as you can? That's fine as well. Whatever works for you works for me. You have to be happy and confident with what you're doing. All right, next. 32 to the negative 3/5. So I'm going to go 1 over 32 to the 3/5, making that positive. So that's going to be 1 over the fifth root of 32 cubed. Okay, well, let's look at 32 again. 32, 2, 4, 8, 16, 32. Okay, so isn't this fifth root? 32 is 2 to the fifth power. 2, 4, 8, 16. Yeah, 2 to the fifth power. But that's raised to the third power. So this equals fifth root of 2 to the 15. Well, heck, there's 15 2's. I need sets of 5 to pull out 1 2, so 15 divided by 5 is 3. So I got 2 cubed, which equals 8. Hope that made sense to you guys. Next, 9 to the negative 3/5. That's 1 over 9 to the 3.5, not 3/5, which is 1 over 9 to this 3.5, so that's going to be 7/2. This equals 1 over the square root of 9 to the 7th. Well, this breaks down into square root of 3 squared to the 7th. Why? Because 9 is 3 squared. So that becomes 1 over the square root of 3 to the 21st. Maybe I should learn how to multiply. 3 to the 14th. There's 14 3's in there, and it's in a square root. So I'm looking for sets of 7. So there's 2 sets of 7. So I'm going to have 1/9. Why? Because 3 7's come out as a 3, another 3 7's comes out as a 3, and 3 times 3 is 9. That'd be 1/9. Okay? Let's get a little bit crazier. All right? Let's do this now. We're just going to distribute. Don't stress out. I don't want anyone to stress out. Okay? This is really, really simple if you just think about it. Let's distribute this to this and this to that. So I've got negative 8x to the 2/3 times the square root of, actually let's make this square root of half already, xy to the half times 2/3. Because remember that square root is the same thing as a rational exponent of 1/2. So okay, this bad boy here, I've got the cube root of 64x squared times, these two's cancel, so I got the cube root of xy. This is good. I got cube root and cube root. Let's multiply them together. I got the cube root now of 64x cubed y. 64, that's going to be 8 times 8. And the cube root of 8 is 2. So this is going to give me 4x to the cube root of y, which is left over. For anyone savvy out there, you could have also known that the cube root of 64 is 4 right off the bat. The x cubed, that comes out as the x, and I'm left with the y. All right, next. Let's go ahead and distribute before we do anything else, okay? Distribute before you do anything else. This is 16 to the negative 3/4 times y to the 24/4. Because remember, there's a little denominator of 1. 3 times 8 is 24. 4 times 1 is 4. So this is going to be 1 over the 4th root of 16 cubed times y to the 6th. Okay, 16 cubed here. 16 cubed here. Let's think about this. I've got 3 16ths. So that means 4 and a 4. 4 and a 4, and then a 4 and a 4, which breaks up into 2 and a 2, and a 2 and a 2. Okay, check out what I did here. I'm looking for sets of 4, right? So I got y to the 6th in the numerator. I got 1, 2, 3, 4 4s. That comes out as a 4. Then I've got 1, 2, 3, 4 2s. Comes out as a 2. So I'm going to have y to the 6th over 8. Would be my answer. Y to the 6th over 8 would be my answer. Okay. There could have been easier ways to do this. For example, you could have done this. 16, that's 2, 4, 8, 16, that's 2 to the 4th power. So you could have gone 4 times 2 to the 4th raised to the 3rd, which is the 4th root of 2 to the 12th power, and 12 divided by 4 is 3, 2 to the 3rd is 8. Either way, several different ways to skin this cat, my friends. Okay, let's distribute again. 8 to the negative 1/3 times x to the negative 5, because 15 times 1/3 is negative 5. So both of them is going to go down in this case. It's going to be 1 over the cube root of 8. Times x to the 5th. Because I don't have a rational exponent there. It's a whole number. So I'm golden. The cube root of 8 is 2. So I've got 1 over 2x to the 5th power. Last but not least, remember, distribute to the 9, distribute to the x, distribute to this 4th root of y. So I would actually, if you want to make your life easier, go ahead and do this. This is 9x y to the 1/4, all to the 3 halves. So this is 9 to the 3 halves times x to the 3 halves times y to the 3/8, which when I simplify this is the square root of 9 cubed times the square root of x cubed times the 8th root of y cubed. It's all in the numerator, so we don't have to worry about rationalizing, but we do have to simplify. Let's look at this 9. 9 is 3 squared. So 3 squared raised to the 3rd power, that's going to be 3 to the 6th. Square root of 3 to the 6, I have 6 3's. I'm looking for sets of 2. So that means 3 3's can come out. So 3 cubed is 27. Times the square root of x cubed, one set of 2 can come out. And I have 1 left over. So times x square root of x. And here, 8th root of y to the 3rd, I can't do anything about that. So times 8th root of y to the 3rd. So in the end, your answer could be 27x square root of x 8th root of y cubed, or probably more commonly, more professionally, you're going to have to multiply these x's, right? So convert them. X times x to the 1/2 times y to the 3/8, which will then give you 27. X to the 1 times x to the 1/2 is x to the 1 1/2, which is x to the 3 halves times y to the 3/8. And finally, if you wanted to put that in radical form, it'd be 27 square root. No, you don't want to put it in radical form because then you're going to go ahead and reduce again. Yep, this is the final answer right here, my friends. This or this simplified, either one. And I hope that made sense to you guys. Again, I know you've been having to learn this, without having the benefit of asking me questions. I hope that I went slowly enough. I hope I gave you enough different strategies, and I believe in you 100%. Thank you very much. Have a wonderful day, and God bless you. Bye-bye.